So welcome everybody to today's Rencontres théoriciens. Today we are happy to have Ulf Danielsson from Uppsala University who will tell us about the journey out of the swamp riding a dark bubble.
Yeah, thanks a lot. It's always nice to be in Paris. Yes, what I'm going to talk about is based on a series of papers, and well, 4 papers so far. Well, there are a couple of other ones, but these are the four with these authors that I've been co-author to, and there are other papers which will appear soon. Now, what we have been trying to do is to address the problem of finding de Sitter in string theory. And I mean, the story goes all the way back to the end of the 90s, where dark energy was discovered. And until then, almost nobody thought that de Sitter would actually be something that you would need to worry about. And historically, most work on quantum gravity was really about trying to prove why a cosmological constant had to vanish. And if anything, at that time, string theorists were preoccupied by studying a negative cosmological constant, an ADS, which seemed to be very natural from the point of view of string theory and maybe quantum gravity in general. But then dark energy was discovered, and we had to rethink within the field. Well, then the quest for de Sitter got on its way, and in the beginning of the new millennium, it seemed to be, well, after some struggle in the beginning, it seemed to be actually quite simple to find de Sitter. I mean, we have lots of different building blocks in string theory, and maybe we could even have a multiverse of possibilities. And KKT is, of course, one of the most prominent and successful attempts, as it looked at least, in constructing de Sitter universes. And it also changed the attitude to string theory completely. Instead of trying to find a unique theory which could explain all the various coupling constants of nature, the idea of the anthropic principle and the multiverse became popular. But then, of course, you might worry, could you get anything? Can anything be obtained out of string theory? Well, maybe not all low-energy field theories can be UV completed and part of quantum gravity and string theory. Maybe there are indeed constraints and observational consequences. And clearly, even if you believe in the multiverse, you must hope, at least, that this is the case. So that the landscape corresponding to theories which can be obtained from string theory should be just a part of all conceivable low-energy field theories, and those which were not in the landscape should be part of the swampland. Okay, well, evidence then accumulated over let's say the last 10 years and even more suggests that it might not be so easy to find de Sitter in string theory. And I wrote a review about that together with Thomas van Riet a couple of years ago, suggesting that there are various problems with KKT and other constructions. And of course, we also now used to think about the swampland very seriously, and the swampland conjecture, which actually tells us that maybe there are not any true de Sitter vacua at all in string theory. And again, if there is difficulties in matching nature, one should actually take this as good news, since it also means that string theory might be more predictive and, of course, more easy to falsify. And in that sense, the bigger the swampland, the better it is. But what if there are no de Sitter vacua at all, as predicted by string theory? How can you then get dark energy? What if the swampland conjecture actually is true, and these difficulties of finding de Sitter is something which has to do with a fundamental issue of string theory? Well, before drawing such conclusions, I think it's important to investigate a little bit more carefully the various ways that you can imagine to embed a de Sitter vacuum into string theory. And it has much to do with whether you accept time dependence at the fundamental level or not. So typically, when we think about de Sitter, we think of a time-independent vacuum. We think of a constant cosmological constant, which is just sitting there. And we do not really act as cosmologists and astronomers, but we rather think of a static configuration. We have static coordinates in the back of our mind. And at the fundamental level, there is no time dependence. It's only through geodesic motion in this static metric that we can accommodate the expansion of the universe. Another point of view, which is of course from a geometric relativistic point of view equivalent, is instead to have the Friedmann-Robertson-Walker metric in the back of your mind, a time-dependent metric, and then say that actually this is how we are supposed to be thinking of things. It's really a time-dependent background which we should embed into string theory. And this makes the intuitive conceptual picture of what's going on very different. And that is sort of the frame of mind that I want to use in this lecture. And then the natural picture to have of what's going on is, of course, the standard popular science book picture of the expanding universe. It's just an expanding bubble. And if you want to embed this into string theory, it's very natural to consider a bubble of true vacuum nucleating in an initial false vacuum. And since ADS is something which you easily get in string theory as it appears, it's natural to think of a non-supersymmetric ADS vacuum, which decays into a more stable, supersymmetric, possibly, ADS vacuum. And the suggestion is that we are living on a brane world which is separating these two different vacua. So it's a phase transition. So we, instead of being troubled by the instabilities in string theory that seems to make it very difficult to construct a fundamental de Sitter vacuum in the usual sense, we make use of the instability and make it something which we actually is part of the construction. So the idea is that we are living then on such an expanding brane world. It's important to distinguish this from the standard Randall-Sundrum construction, which you also can, if you wish. In Randall-Sundrum, you can also think of bubbles being, or brane worlds being embedded, but there you have a symmetry across the bubble, and usually you can think of it as being a junction between two insides, and it naturally leads to ADS on the brane world for extremal branes. Now, the good thing with Randall-Sundrum is, of course, that 4D gravity with its gravitational modes is localized close to this brane world. Now, we are doing something very different. We have something which, in a sense, is much more simple and easy to visualize. It's a bubble with an inside and outside, an expanding bubble with an inside and an outside. And as we will see, the junction conditions automatically leads to time evolution. The bubble is expanding, and an induced de Sitter metric. An important thing is, of course, that gravitational modes cannot be localized in the same sense as in Randall-Sundrum. This is something that you might worry, but I will try to argue that you still get 4D gravity from an effective point of view, and this will be a big part of my talk to describe how this happens. But again, the key is the junction conditions, the Israel junction conditions across a thin shell where the extrinsic curvature jumps by the energy momentum tensor which sits on the shell. It's also very important to keep in mind that our brane is not a probe. It's not that we have a fixed background in which the brane is moving. The gravity induced on the brane is induced because of the back reaction on the background. So in fact, we have different backgrounds on the two different sides of the brane. It's a phase transition. and the shift in the background energy of the 5D vacuum is what feeds into this, into determining the strength of the four-dimensional Newtonian or even Einstein gravity. So let us take a look at the junction conditions. So here is the junction condition, which is actually just the difference in the extrinsic curvature between the inside, denoted by a minus, and outside, denoted by a plus. And A is the radius of the bubble, and it's here written in terms of the induced proper time on the shell. And sigma on the left-hand side is the tension, and you see the five-dimensional Newton's constant there as well. And we have different values of the cosmological constant, the negative cosmological constant on the inside and the outside, and the vacuum is deeper on the inside. And note the minus sign. The minus sign has to do with the fact that you have an asymmetric bubble with an inside and an outside. If you have Randall-Sundrum, then you have a plus sign because there's a symmetry between the inside and the outside. Now, this is just with the bubble which is sitting in a pure ADS background. You can also consider having a short-chilled ADS. So you have a mass parameter M, and this mass parameter can in principle be different on the inside and the outside, as you will see. Now what we'll do is that we will be considering a very big cosmological constant. So it's microscopic physics, it's high energy physics that determines the cosmological constants of the ADS5. And we will not necessarily need, we also, of course, we have extra dimensions above these 5 dimensions. They need not be scale separated. All of these extra scales are small compared to the energy scales are high compared to the physics that we are discussing on the brain. So what we'll be considering now is a small Hubble constant, a small curvature, and these corrections will also be small compared to k squared, and then we'll make an expansion of this expression for the junction conditions. And what we obtain is something that looks exactly like the Friedmann-Robertson-Walker metric, the Friedmann equations for the FRW metric, where we can read off, in particular, a cosmological constant, a 4-dimensional constant. And you see here that, of course, the tension of the brain needs to be smaller than a critical value in order for the bubble to be able to sit there at all with a positive curvature, and it implies a positive cosmological constant by construction. We can also read off the effective 4-dimensional Newton's constant, which is related to the 5-dimensional Newton's constant, and then we also have the k minus and k plus. We see here that if we have a plus sign and a minus and the plus, the k minus and k plus are equal, then we recover the Randall-Sundrum expression. But we have different values of k minus and k plus, and we have an inside and outside, and hence this minus which is sitting there. And we also see that the black hole metric on the outside, it also induces something which effectively looked like radiation. So from this point of view, we seem to have been able to recover something that looks like a decent cosmology. And we will study this in much more detail in a moment. Let me just first again make a comparison with Randall-Sundrum. So here we have, this is where we are, we have the inside outside, and we see that when we increase the tension, then the 4-dimensional CC goes below 0 and we cannot have a bubble in the same sense. And then here we go to an inside outside, and if we increase the tension even more, then we can recover a positive cosmological constant also on Randall-Sundrum. But this is where we are, and this is how the designs work out for us. Okay, before studying this more carefully and how you induce gravity and in the property of the physics on top of the brain, let me make another connection, which I think supports this picture also from a quantum point of view. And that is that we can see how the cosmological horizon can be explained as a Rindler horizon. Now, we know that contrary to a black hole horizon, the cosmological horizon is observer dependent. And even that would suggest that maybe there is a connection with the Rindler horizon, which is also observer dependent. But clearly, if you're stuck in your 3+1 dimensions, you cannot just by accelerating mimic a cosmological horizon because you will be selecting a particular direction. It's different if you now have the possibility to accelerate in the 5th dimension. And our proposal is, in fact, that what our construction is telling us is that the cosmological horizon actually is a Rindler horizon in 5 dimensions. And you can see that by calculating the proper acceleration in our background. And then you can see that for a bubble, which is expanding like it has a exponentially, so it corresponds to a constant 4-dimensional cosmological constant, we see that the proper acceleration squared is k² plus h². Now the en route temperature or the Rindler temperature in ADS is not just acceleration divided by 2 pi, but the proper formula has the acceleration squared minus k². So there is a critical acceleration, which if you have global coordinates and you are sitting at a constant radius, then you are accelerating. But if you just do that in empty ADS, that does not give rise to a temperature. You have to accelerate more than just keeping your distance to the center of global coordinates. And you see that the excess is just given by h² and you get h. So in fact, the Rindler temperature for this accelerating expanding bubble coincides with what you would naively calculate as the de Sitter temperature by doing some 4-dimensional analog of the black hole discussion for the temperature of a black hole. So even already at this level, there is an intriguing connection between the cosmological horizon for such a bubble and the Rindler horizon. So we would say that somehow this model makes sense, at least at this level. Okay, now how do you get matter? Well, an important point is that matter is not localized on the shell. And that also has to do with the fact that gravity is not localized as it is in Randall-Sundrum. And in fact, to get dust, just massive particles, or if from a cosmological point of view, let's say that you want to have a dust in the FRW cosmology, then you need strings, which are stretching outwards from the brane world and ends on the brane world. And you actually have a cloud of strings, that is this corona-like picture I had in the beginning, string stretching outwards. And the point is that what these strings are actually doing, they are there in order to effectively compensate for the reduction in energy that you otherwise would have due to redshifting. If we go back down here, then you see that if you have just to have a metric which just goes like m/r², it leads to radiation. If you want to compensate the 1/a4 and get the 1/a³, so it's like dust particles, you need to have an extra an extra linear dependence in the mass parameter. So it goes like 1/r instead. And that corresponds to having a cloud of strings, so it's not empty outside of the brane. It's actually strings which are stretching outwards. And then you can mimic in such a background, you can mimic cosmology with dust particles. You can also do this a little bit more carefully by considering strings with a particular tension. And you can see that such a homogeneous string cloud, such explicit solutions exist. You can see then how this parameter in the metric, now going like 1 over r, not 1 over r squared, how this parameter is related to the number density of these strings at the position of the brane and the tension. And by seeing what kind of cosmology this leads to, we can actually identify that the mass, the effective mass of a particle, which actually is a string which is stretching outwards, is given by the tension of the string divided by k, which determines the cosmological constant, the ADS, in the ADS space outside of the brane. Actually, we can see also, I will mention this briefly later on, how you can see this not only in a cosmological setting, but also if you look at a particular single string. But we'll come back to that in a second. So the space exterior to the bubble now, another important thing to realize, it need not be infinite. It's not that we necessarily think on this bubble to expanding in an infinite ADS space. It can be cut off, and the strings might be ending somewhere. But as the bubble expands, it sort of eats these strings, and in a sense, these strings are pulling their endpoints upwards as the bubble expands, and it looks like massive particles from the point of view of someone living here. But again, this size of the throat can be microscopic, even though the coordinate radius and the area, the volume of this shell, I mean the volume, the three-dimensional volume of this boundary here is very, very large, or astronomical. And that has to do with the fact that the proper radius of the universe does not increase very much over a Hubble time. And this has just to do with the fact that we are in an ADS space, and we have these huge blue shift factors as we move upwards and the bubble gets bigger. So we can actually conclude here that even though the universe is expanding over a Hubble time and the coordinate radius is increasing a lot, the proper distance that the bubble is moving in the fifth direction is still only the ADS radius, which could be tiny. And it means that you can fit all of this into a microscopic throat in an ordinary string compactification. It's not that we have to have this embedded into a very, very huge ADS space, because it's actually a very, very slow motion due to these blue shift factors. Okay, so the idea is that we have something like this. We have the brane expanding, and we have these strings which are pulling their endpoints as the universe expands. Now, is gravity really Einstein? I mean, we have been looking at cosmology and the Friedmann equations, but as you know, the Friedmann equations you can obtain by a simple Newtonian analysis. It's not necessarily so that this must correspond to true Einstein gravity. But there are various ways to see that this is actually the case. One way to do that, which works very well in the cosmological setting, is to use the Gauss equations, which relates the 5-dimensional Riemann tensor to the 4-dimensional Riemann tensor and the extrinsic curvatures as you jump across the shell. So this is how it looks like on the outside and on the inside. So we take this as a starting point. This is a much more general, much more powerful equation than just the Israeli junction conditions that I wrote down, but of course they contain them. Okay, so this is our starting point. And then we consider an expansion around an extrinsic curvature, which corresponds to having just this critical shell. So we have small perturbations relative to that. So we have an extrinsic curvature, which is just k times the induced metric. And then it turns out that this Gauss equation can be written in the following way, where we have arranged things so that we on the left-hand side have the four-dimensional Einstein tensor, and then this is what we have on the right-hand side. And you see here how you get something here which looks exactly like a four-dimensional energy momentum tensor. And it's very crucial that you get the factor 1/2 here. Sometimes, I mean, when you try to do, you try to embed let's say four-dimensional gravity in a higher dimensional setting, you get the wrong factor here because you inherit structure from higher dimensions. But that is not true here. Here you get actually the crucial 1/2. You don't get a 1/3 or maybe something else that a higher dimension might cause. In 5D you have a 1/3, but you do get the 1/2 here for the matter tensor, and it's related to the properties of the 5-dimensional space-time and its metric. And we can now consider this special case, which we have been looking at, where you have this piece, which yes corresponds to a Schwarzschild black hole, which leads to radiation. And you have this piece, which is a string cloud, which leads to matter. And indeed, when you plug these in, you get exactly the Einstein equations with a cosmological constant, with appropriate value. This is just what we had before. We have identified the four-dimensional Newton's constant in particular here. You get radiation for the 1/4 with the correct with the index, the correct structure here with energy and pressure, and you also get dust. So it's actually the four-dimensional Einstein equations that we obtain in this construction. So this we think is a quite non-trivial result. Let me go on and talk a bit about localized matter, because here again we see the importance of the stretched strings. So if we have the brain sitting here, you can imagine doing various things. You can just put something here on the brain and then it will zag down a bit. But you can also have a string which is pulling, and then the brain will pull up like this. And the point is that if you have just some matter which is lying here, that is just like if you were to increase the tension of the brain, for instance, that actually goes in the direction of reducing the effective energy density. So if you want to have a positive energy density on top of the brain wall, as viewed from 4 dimensions, as interpreted from the point of view of the Junction conditions, you have to have a string which is pulling like this. This we have seen before. We have seen that a string cloud leads to dust particles in a cosmological setting, and hence a localized mass should correspond to a pulling string. And the pulling string means that the brain is going up a bit like this. Okay, let us see whether we can recover a localized metric from a massive perturbation in 4D. Well, the metric will be affected by the bending of the brain. So we have, in the presence of a bending, we need to see what kind of 5D metric we can have. And what we are looking for is a cylindrically symmetric metric. And what we do now, because we are considering far away from any source, we are off the brain. The brain might be bending, but we are looking for something, the metric of that bending brain. And what we can choose, at least far away from the string, is a transverse and traceless metric. So we consider now a linear order small perturbation of the ADS metric, which we have here. And it's traceless and transverse and parameterized by a small parameter chi. And you see that this is the time and radial and the angular components of such a perturbation. Now, if we now consider large distances, so large proper distance, and z times r, you see it here. Z, this should be a Z squared here, sorry, Z squared times R squared. ZR is the proper distance. So when that is big, there is a simplification. And actually at large proper distance, the metric starts to look like this. But the brane is bent. It's bent by the pulling string. So the induced metric will get the contribution from the fact that the 5D metric is affected, and the fact that the brane is bent by the pulling of the string. And that induced metric has to be Schwarzschild and solve the 4D Einstein equation, since we are arguing that by consistency, and as we have seen already from the cosmological point of view, the induced metric, it has to solve the 4D Einstein equations. And that means that we can identify the parameter chi with the mass m so that we get the Schwarzschild metric. And what we have done then is to self-consistently, we have this string which is pulling on the metric, on the brane is bending, affecting the surrounding space-time, and the induced metric is such that it solves the 4D Einstein equations. Then we have a consistent solution to the system with the string pulling on the brane. Okay, and by the way, this again, which I already argued, that this also explains the signs in the contribution to the energy density. There's a minus sign there, but the thing which corresponds to positive mass is things which get the brane to move up. So we really need these pulling strings. Okay, now that was a single string. But a very important thing to address is, of course, if we have several strings which are interacting with each other. And here we will see a crucial difference between our construction and the Randall-Sundrum, and it has to do with the fact that gravity is not localized on the brane, but nevertheless, the system reproduces four-dimensional physics. So let us consider two strings which are stretching radially outwards. And it's very convenient to think of this bubble as having a finite curvature. So you have these strings stretching outwards like this. Now, if nothing happens to the strings and they are just sitting there, ignorant of each other, then as the universe expands, then the proper distance between the strings increase. And this is just the expansion of the universe. It just means that these endpoints corresponding to point particles, they are just carried by the Hubble flow, and as the universe expands. So when the universe gets bigger, then the proper distance between them is larger. The universe is eating these strings as it expands. But now let's assume that we ignore the expansion of the universe for the moment and instead focus on gravitational attraction between two particles. Then in order for this picture not to completely just break down, the strings need to be moving in sync, remaining stretched as they are attracting each other in order for this to, in a consistent way, reproduce the four-dimensional gravitational force between the endpoints of these strings. Now, let's see if this can work out. We consider the Nambu-Goto action for an embedded string in the background of another string. And the background of the other string, the 5D background we already had, that is at least far away from the string. There will be corrections where you can close into the source, but this is the far out metric, which we obtained from the studying the bending of the metric. Okay, so we put that in here. And we consider now straight strings. And we can also see from these equations that the string remaining straight is actually a self-consistent solution. It basically means that stretching the string will cost energy. And a straight string is solving the equations obtained from the Nambu-Goto action, and a string which is radially stretching and then moving in angle, just like this. And we can see that the equations of motion from here yields this equation from the point of view of 5D. But then, of course, we need to calculate what happens to the endpoints, actually. So what is the induced motion of the string on the brane? And when we do that, we recover exactly the expected gravitational force. So we see that self-consistently, the strings are moving stretched like this, and they are swinging like this, and their endpoints are following four-dimensional physics. This, of course, means that the gravitational force down here must be equally big as up here. So all of these segments of the strings are attracted with the same force, even though the distance up here is bigger than it is down here. And this is exactly what this metric actually tells you, that this is indeed the case. And furthermore, you can also see this by making contact with the distinction between normalizable and non-normalizable modes when you solve the gravitational equations in 5D. And here again, you will see a very important distinction between what we do and what you do in Randall-Sundrum. So in Fourier space, if you solve the equations for the perturbation of the metric, you basically get two solutions. It's the K2 and the I2 Bessel functions, where the K2 will be diverging when A goes to infinity, but it goes to 0 in the other direction, and it's reversed basically for the I2. And in holography, you talk about the bad non-normalizable mode and the good normalizable mode, respectively. Now you can note that the Fourier transform of K2, then you get this, and this should ring a bell if you really carefully looked at all the equations, because this is this guy. So this is nothing else than the position space version of the non-normalizable solution for the perturbations. And here you have everything in terms of here it's the full index structure and not just some toy model just with a scalar field. But this is really the position space version of the K2. So this is really the non-normalizable choice. Apparently, we have chosen the non-normalizable mode. And the reason that we can do that and should do that is because these strings are stretching all the way up and are sourcing gravity all along. So there is no inconsistency in that. Now, this makes it very different from Randall-Sundrum, because in Randall-Sundrum, we have everything is localized to the brane. You have a K2 on the inside, and then you just have a reflection on the other side. So it's one inside, another inside. So it's sort of a K2 going up like that, and another identical K2 moving up in that direction. You have localized gravity, and you get, by studying this system, you can also calculate the induced propagator from here, and that propagator corresponds to the propagator of four-dimensional gravity. And you can also identify the Newton's constant, how the G4 is related to the G5. That you can do in Randall-Sundrum. We can do exactly the same thing, but you would be tempted maybe at first to say that, okay, I choose a K2 on the inside and I2 on the outside, corresponding to a normalizable mode here. But then if you do the same analysis as up here with a K2 and I2 and look at the resulting 4D propagator, it's wrong. It has a completely wrong structure. It cannot be. While the correct choice is again to use the K2 and the K2. But the K2 here on the outside will be growing, but it leads to the correct propagator, and it's also consistent with these strings which are moving like this. But on the other hand, gravity is not localized, which, well, there is no problem with that, of course, since it shouldn't be localized because the strings are stretching all the way out. And I should emphasize now that if you're somewhat unsatisfied with this analysis and the discussion for the single strings, is there something fishy going on here, then just go back and think about the cloud of strings in the setup, in the cosmological setting, where it's absolutely clear that you get an induced 4D gravity in this cosmological model with the string stretching all the way out and the bubble expanding, eating these strings. So this discussion is supported and consistent with this cosmological analysis. Now, furthermore, another way to see why the non-normalizable mode makes sense here is to consider starting with the string, which is going all the way down here in ADS, and then you have a spontaneous nucleation of the brane. Now, the spontaneous nucleation of the brane is invisible from up here just because of energy conservation. So it cannot be seen. There is no change in the total energy from a holographic point of view. That means that there cannot be any normalizable mode excited. And then the only way for this brane to be able to sit there and for the junction conditions to be satisfied is that there is something non-trivial going on with a non-normalizable mode. So you see here that if you have a string going down here and you put in the brane and you don't want to touch energy conservation, and this is just mirroring what we are doing in the cosmological setting, then to match the junction conditions, where you in principle have the choice, so you can balance normalizable and non-normalizable modes. But now you're not allowed to fiddle around with the normalizable modes. You have to put in the non-normalizable modes. And then everything is, as we argue, self-consistent in this picture. You can make further holographic allusions here and say that close by, if you look at really tiny short distance, you're probably not looking at 4D gravity at all. You need to feel the presence of the brane in order to be able to claim that you have 4D gravity, and cosmology will be on even higher scales. Okay, now I'm sort of going towards the end of my talk here. The way that you can understand the difference between what we are doing and other things that have been done is by sort of classifying different ways of hiding extra dimensions, let's say. I mean, in ordinary compactification, you think of a particle which you smear quantum mechanically over the extra dimension. There is no momentum in extra dimension, its wave function is just smear, it's just constant along the extra dimension. Okay, that's one way. Randall-Sundrum, there you have sort of a quantum localization on a brane, and the wave function is rapidly decreasing when you go away from the brane. With our dark bubble, we have simply a string which is classically stretched over the extra dimension, but its motion is nevertheless described effectively as 4D. It's a kind of a projection in 4D. You can specify all the low energy physics by using a 4D language. Now, again, this string need not stretch infinitely far. It could just be part of a throat of finite length. It could even be that it connects back to another brane a bit further away. You could even think of a sandwich, which is separating two different ADS space, and the strings are moving within the sandwich. That would be one possibility. And perhaps our whole picture is actually much closer in line with thinking of a compact dimension with a single wrapped string, which then is moving along with that. can then be moving in the big dimensions, but it's just stretched around the extra dimension. So it's a bit closer to that in a sense than these other ways. Okay, so this is actually my last slide, and I just want to discuss a little bit what to do next with this model, how to test it. Is it really physically consistent? Is it useful or whatever? Well, one thing is certainly that you would need to fit the early universe. You need to study the physics of the nucleation of this bubble. And actually, it's very similar to an nucleation of the universe out of nothing. In a sense, mini superspace becomes the scale factor of mini superspace in a Wille-de-Witt approach, a quantum cosmology approach, just becomes this extra fifth dimension. So then what we would like to study, and I'm working on this together with Thomas van Riet in particular, trying to understand what's going on in the early universe, and particularly make a connection to the dark bubble and quantum cosmology. Another very important issue, and perhaps one of the most important ones, is of course to find a true stringy realization of the whole model with a small cosmological constant. I mean, that was the whole motivation for doing that. I mean, claiming that what has been done so far, including KQLT, might not actually work, but this should in some sense be better. What is good with this model, I think, is that it so naturally gives rise to a positive cosmological constant. The only thing that you actually need is an unstable ADS5. You might not be able to tune everything to a small cosmological constant, but as soon as you have a non-perturbatively unstable but perturbatively stable ADS5, you are more or less there. So one needs to understand much better whether there are non-perturbatively unstable but perturbatively stable ADS5 space-times, and hopefully a set of such space-times where you can also tune various parameters. But from what I have learned, it's not as much known about this as one would have hoped. Okay.
Ulf,
yes.
Sorry, one question.
Yes.
By non-perturbably unstable ADS5, you mean one that's unstable against Coleman-de Lucia instantons?
It should be either that, it should be non-perturb. It should be an instanton decay. It could be with respect to fundamental branes also. And one could imagine, I guess, a supergravity theory where the vacuum is non-perturbatively stable, but then you have to put in from string theory a fundamental d5 brane or an NS5 brane or something which is mediating the decay. But the important thing is that it should be non-perturbative. It should be a non-perturbative instability. It should not just be a perturbative stability. It should really be a second order transition. Okay, and then we should also make contact with the standard model. We have made a few comments on this in one of our papers, but in particular, we would like to understand like electric interaction. Let's say that these strings are charged. What would happen then? Well, then clearly in the 5D space-time, we should not only look at metric perturbations that leads to gravitational force, but you should also look at tensor forces. So you would expect to have a two-form field, like the B field or a Ramond field, that also have a non-normalizable mode and would in that way make sure that these strings can be attracted or repelled electrically as well. So that's something else that you would like to introduce into the theory. And in some sense, I mean, you have to reconstruct many of standard physics from scratch in a way. And it's not clear how you would the connection with just ordinary quantum field theory, because we do not have a quantum field theory, a 4D quantum field theory that is living on the brain, but it actually involves the physics, the bulk physics in 5D. And maybe you would even need to go to string field theory in order to, and start there in order to reduce it down to a 4-dimensional field theory. I'm just saying this just to emphasize that it's not obvious how 4-dimensional quantum field theory is extracted out of this construction. Nevertheless, if it's embedded into string theory, and what I've said so far makes sense, then it should be there. It should be there more or less by construction. Now, you could also imagine quantum effects that would change the effective cosmological constant, because this brain, it could be excited, it could be a black brain, it could be a brain which have a tension that might change in response to temperature, like tachyon condensation on top of it, for instance. And here there might again be a connection to the swampland. So even though it looks like this bubble would classically be expanding just forever, it could be quantum effects that eventually will kind of a friction that will stop this expansion, and maybe it will recollapse again. So these are things that we also would like to study. And then clearly we would like to incorporate black holes into the picture. How would a 4-dimensional black hole actually look like in this construction? So that is something else that we are looking into, and also making contact with some other earlier work that we have been involved in. But this is something that is very tricky, but seems to be very interesting. Okay, that's it.
Okay, so thank you very much. I think I will applaud for everybody. So are there any questions?
I have a question. This is Stefan Mancas. Can you explain periodic universes and also collapsing universes through this model?
Well, I mean, in principle, it's a collapsing universe is in principle easy if you have a positive curvature. So since we have a positive curvature and a cosmological constant, and if we are not necessarily want to compare with the real universe and have control over the size of the CC or anything, it's very easy, because if you have a positive curvature and the cosmological constant and nothing else, then you easily just get the bounce. And this universe will be nucleating. If it's tunneling out of something and then nucleates, it will nucleate at its smallest possible radius, and then it will expand. You could equally well think of a bubble which is contracting and then bouncing back out again. Now, in our universe, of course, we know that is not the case, because if you look at the effective potential, our universe is traveling above this static Einstein universe. If it had been below, we could have imagined that our universe had been bouncing out. We now know that is not the case. So then we have to follow it further back in time, and then we would have to have a cosmological constant that is increasing in order to get the bounce and so on. So, I mean, the only thing I'm saying is that in principle, yes, with a positive curvature, you can envision a bounce. But in order to make a sort of realistic theory of the early universe, I don't know. And I mean, clearly there are lots of problems with that. But in principle, you can have a bounce with this bubble.
How about the periodic universe?
Well, then you would need it to come back down again. And since we are, if you look at it classically, just taking this literally, we have a universe which is expanding forever. I mean, if we put in even if we put in some radiation and let it nucleate, then it will just expand forever, unless there are some other effects like this quantum effect that I was talking about that might sort of prevent it from expanding forever. But classically, it's very natural for it to just I mean, it's difficult to get oscillations. A bounce, it's much easier to get, but to get both, I mean, again, if you think of it, if you think of the effective potential, if you have curvature and the radiation and the cosmological constant, then you just look at the Friedmann equation. You can get something which is bouncing and go back out again, or you can have something which is expanding and then recontracting and then crunching. But you cannot sort of have both of these turning points in the same model. They are on opposite sides of the hill. So coming in from infinity, bouncing, going out to infinity, that's easy to imagine. A universe which is expanding and then crunching back. That's also easy.
Thank you. Yes.
So there is a question from Germain Rousseau. I think you can unmute yourself and ask the question directly. He asked the question in the chat, but Germain, can you hear me?
Yes.
Okay, go ahead.
Ulf, will the bending of the brain by the string induce some dissipative phenomena of any kind, which are not taken into account usually by JR?
That I don't know. I mean, you would think that the brain could sort of vibrate, maybe, or something. I'm not sure. I'm not sure whether that would correspond to gravitational radiation or not. I'm not sure.
Okay, thanks.
But that could be a possibility that it would. I mean, if you look at the equations, as long as the energy densities are small compared to the scale set by ADS, then it looks as if you have pure 4D Einstein gravity. But as soon as the energy densities are big enough, there are higher order terms in the energy density. But it's only when you get to really high energy density set by this high energy physics scale. So at high energy densities, I'm sure there will be corrections to 4D gravity, which can be extracted out of the junction conditions. So maybe that could yield something.
Thanks.
Hi, Ulf. I have a couple of questions.
Yes.
The first is, in a sense, related. At long distances, you say you have 4-dimensional gravity. At short distances, you should have 5-dimensional gravity. At what scale does this transition happen in terms of your other scales?
Yeah, okay, good. The thing is that the metric that we have written down is at large distance. And I can also tell you, to be honest, that when we looked at the bending of the brain, we have only calculated this to leading order in m/r. And we are technically struggling to see how we can go beyond that. And that is sort of taking steps towards even embedding a black hole into this structure. But what is absolutely clear is that there will be corrections to the metric when the distances are small enough. And in fact, we can just go back here and look at the metric here, the metric over here, where we actually see such corrections. And these corrections set in basically when the distance to the black hole, to the source or whatever, is of the order of the higher dimensional ADS scale. So that scale is very important. And you can also, of course, it's the same sense here with the K2. And then you can see also that there's the same story in the Rundle-Sundrum, that there are corrections when you're close to the higher dimensional ADS scale.
But you have two ADS scales. Which one is the relevant one, or is it the difference?
I think it's, I would probably think that it's the scale, the lowest of the two that will come in.
I see.
Then it could be that they're, I mean, we don't know whether they are roughly, they could even also be roughly equal. I mean, a crucial equation in our whole setup is, of course, this one that relates the 5-dimensional Planck length to the 4-dimensional one through this. And you see here that depending on the relative sizes of this K minus and K plus, there's a certain interplay between these scales. But from the way that we look at it, then all of these scales are high energy physics. Certainly the 5-dimensional Planck scale, but also these scales. And of course, this is the ordinary Planck scale. And this is also needed in order not to get higher order contributions from energy densities, such as this one, to the Einstein equation. So one could in principle, by constraining higher order terms in the energy momentum tensor from observations, one could constrain the size of the ADS. And then, of course, one could try to see what does that mean when it comes to short distance corrections of gravity as well. So that, I guess there are sort of different ways of constraining. Okay.
Okay, I see. There's another thing that you alluded to, but I would like to ask it again, just to make sure I understand. We see 4-dimensional physics when we do experiments, and therefore you would like to understand how on your brain you have some fluctuations, at least, that see at low energy 4 dimensions and not 5. So how do you envisage this can happen?
Okay, so the way that I envision this is that we are, and our experimental apparatus is composed of strings which are stretching out like this. So this is us. So all experiments.
But why you don't see 5 dimensions then?
Because the excitations in that direction is high energy, while the low energy motion is the motion in 4 dimension. Let me just, in order to visualize this, just think the following. Let's say that we are that you have a universe, yes, the toy model, with a compact dimension which is small, and then you have a wrapped string around it. And then that wrapped string is what corresponds to your massive particle. Then you would say then that higher then you can I mean, what you can do is you can dimensionally reduce to 4 dimensions, even if you have a string which is wrapping a higher dimension, a 5th dimension. And in a sense, that is what we have been doing here as well. You can think of this extra dimension as not necessarily being big. It can have a proper size that is very, very small, and you can still fit the expanding cosmology. And that has to do with the fact that you have these blue shifts. When you actually calculate, like here you have the brain expanding a Hubble time. It doesn't matter what the scale is here. While doing that, you are still not moving further than an ADS radius. So even though, I think that it's wrong to look at our model and in your head have a picture of a big extra dimension. Actually, it can be as big as you like, because nothing depends on that size. But if it feels better for you, then you should think of it as small. And then you should also be perfectly clear that there cannot be any 5D physics that might be at too low energy and disturb your four-dimensional point of view. So maybe the short answer would say that no, the extra dimensions need not be big in size, and that's why you don't need to worry about any other physics. It will be at higher energy scales.
Thank you. I have one more question. As you know, some time ago with Francesco and others, we have looked at a setup that is a bit similar, where we have a brane in an ADS, near ADS bulk, etc. We had also scalar fields, and instead of having transitions, let's say, between two ADS scales, you have also the scalars that are running. And in this case, via a general analysis, we got that generically the gravity on the brane is massive. Now, in your case, you find that it's massless. And I wonder what's the characteristic difference in your case that makes it different? Otherwise, boundary conditions are sort of similar to what you're using.
I think that the graviton, I mean, this is something which is okay. I mean, yeah, one can argue like this, and I guess that is what you're saying. I mean, if you look at our results, even if you just look at the cosmological results, what we get from the 4D point of view is what you would get if you have a massless graviton, if you just have ordinary 4D gravity and no mass parameter. So indeed, that does seem to be what we get. Now, where is the graviton? If I really look at the graviton as an excited particle state, then I would say that that graviton is actually spread out through the extra dimension. It's spread out through the extra dimension, and it's moving in that direction. It's not localized to the brane, but it's something that moves in the full extra dimension, in the four-dimensional transverse, four-dimensional transverse direction. I would really like to be able to write down equations describing a gravitational wave and see that gravitational wave as a perturbation in full 5D. That's something, because I would say that also, if I would like to, if you put it like this, let's say that I would like to produce a gravitational wave, then I should use matter. And I know that matter are these long strings. So I should shake these strings, and they would affect the five-dimensional metric in such a way to produce a gravitational wave. That I haven't done yet, but that is something that we should try to do. But again, gravity and gravitational radiation cannot be localized to the brane. It has to involve the full 5D space.
Okay, thank you very much.
Okay, any more questions? If not, we can thank Ulf again.
Thank you, Ulf.
Thank you. Thank you for having me.
Thank you.
Thanks.